All right. Hello, everyone. Today we're going to do a beginning of a data structures segment. We're going to start with hashes and arrays, and hopefully you have a okay understanding of what hashes and arrays are already. We're going to take a look at behind the scenes how they work and how they affect runtime of our algorithms and how we can use them appropriately to get the runtime that we want and solve the correct types of problems with the correct data structure. So let's jump right in. Objectives for today: have a deeper understanding of arrays and hashes, and we're actually going to talk about sets as well because they work similar to hashes under the hood. So we want a deeper understanding of these things, and we want to know in what situations to use our hashes and sets. And at the end, we're going to do a little coding challenge where we work on making a primitive hash ourselves in Ruby for Scratch. So that should be fun. All right, so arrays. All right, so first of all, I'm going to ask some questions during this, so feel free to pause your video and try to answer them yourself. And then I'll take a brief pause in between me asking a question so that you can have time to pause and try to answer, and then we'll go through the answers. Okay, so what are arrays? So on a base level, arrays are actually blocks of adjacent memory in our computer, and they're segmented into indices. Okay, so every element in an array is actually adjacent in memory to its adjacent indices in the array, right? So I like to think of arrays kind of like cubbies back in grade school, right? Where imagine just a row of cubbies on the wall, and you put your lunchbox or whatever it is that you have in grade school in your cubby. And let's say every student has their own number. So it's sending numbers starting at 0, going up to however many students there are in the class minus 1. And these cubbies are adjacent to each other, and they're able to hold your stuff. All right, that's kind of what arrays are like. All right, and so you've probably used arrays in higher level programming languages like Ruby and Python and JavaScript, etc. We're going to talk a little bit about what arrays look like if you're using C, because these arrays are what dynamic arrays in these higher level programming languages are built off of. So understanding how your basic fundamental arrays work can be useful to understanding what is happening under the hood when you use arrays in a higher level programming language. So if I'm programming in C, there are a few extra things that I have to do that I don't necessarily have to do if I'm programming in Ruby or Python. For example, I have to specify what type of data will be inside of the array. And I have to specify how long the array will be. And this is important because what my computer is going to do is, once I've specified these two things, it's going to calculate exactly how much memory it has to allocate for this array, and then go find an adjacent memory block of that length that it can then give to you to utilize as your array. Okay, and the elements in your array will be separated in these evenly spaced memory blocks that are adjacent to each other in your computer's memory. All right, so let's start off with an easy question. So if we allocate an array and we put 10 elements in there, and we want to put integers in every single cubby, all right, if your computer, let's say we're going to assume that our computer uses 4 bytes to represent an integer. So how many bytes of data will be allocated for this array? So you have 10 elements and 4 bytes per integer. And we're starting off easy. That's just going to be 40 bytes of data that your computer is going to go out and allocate for your array. All right, and this is important because it gives us a really, really cool aspect of how it works, right? So when we want to retrieve a specific element from our array by its index, our computer can now calculate exactly where in memory this information lives, and it can go directly to that spot. So it doesn't have to look around for it. It doesn't have to do anything extra. It just calculates exactly where in the computer's memory this information lives, and it goes there. So let's try a little example. Let's say that we have an array, and the memory location of the array starts at memory location 100, and we're going to be working in decimal here. Don't worry about hex. So if the array starts at memory location 100, and we have 10 integers that we've allocated for our array, and I want to go to index 2, what memory location will your computer go to retrieve that element at index 2? All right, so pause and think about it, and we're actually going to draw it out and take a look at what this looks like. So, all right, so we have our set of cubbies, okay? So here's our array that I've allocated out. And I'm not going to draw every single index location, but you can get the idea, and then we'll say it goes out to 10 total. So we have index 0, index 1, index 2, index 3, index 4, etc. So if my memory location starts at 100, okay, and I want to get the information here in index 2, right, I want to calculate what memory location to go to so I can get that information right off the bat. So if I know that there are 4 bytes per cubby, right, because I'm representing integers here, then I can say, okay, so element 0 is bytes 100 through 103, and so the end of byte 103 will be the end of element 0, okay, and then 104 will be the starting memory location for the beginning of the element in index 1. And that goes for the next 4 bytes. So we have 104 through 107, meaning that the starting byte location for index 2 is 108. So my computer's going to go to memory location 108, retrieve the stuff in this cubby, or the element at this index, and retrieve bytes 108 through 111, and then the beginning of 3 will start at 112. So 108 through 111 inclusive will be the information that is retrieved that is your integer in index 2 of your array. All right. So, and mathematically, if we want to write this out, so index 2 starts at 100 plus 4 bytes per integer times 2. All right, so index 2 is the third element in our array, but to get to the beginning of it, we have to traverse 0 and 1. So that's why we multiply 4 by 2, and we get the starting memory location of index 2 at 108. All right, so let's talk about if we're using an array like this, this basic array, and see what happens if we make our array longer than what we initially allocated for. Well, remember that the array has to be consecutive bytes in memory. So what actually is going to happen is that your computer, if there's no free memory after the ending location of your array, it can no longer maintain your array as consecutive bytes, but it has to. So what it has to do, it has to go out into your memory and look for a place where you have consecutive bytes that will fit the entire array of this new length, okay? So you actually have to go out and allocate a new memory location that's big enough to hold everything, and then you have to copy over every element one at a time from the old location to the new location, okay? And so this will happen in the higher level programming languages behind the scenes for your dynamic arrays. So it's important to know that this could be happening from time to time. Now, when you make a new array in one of these languages, it shouldn't allocate 0 bytes off the bat. So even if you make an empty array and start shoveling stuff in, it won't happen every time you shovel probably, but it could happen if you exceed the size, which it was automatically allocating it first. So that's an O of n operation, and we talked about time complexity in a previous video. So it should make sense that if I have to take my old array and copy over the elements one at a time, that it's going to be a O of n algorithm to perform that copy of every single element, where n is the length of my array. All right, so let's talk about what arrays are good at, okay? They're really great at doing constant time lookup if you know the index, okay? So there's fast random access. If I know the index where my information lives, so if I know the cubby number, where all my stuff is, I can walk directly to that cubby. I don't have to start at cubby 0 and walk down the line until I find my stuff. I go directly to the cubby I care about and take my stuff out, right? So I calculate the exact memory location I need to go to, and I go there, all right? So what are arrays not good at? Well, they're not great at searching through something. So we talked about before in a previous video how long it takes to search through an array. So if you have an unsorted array and you want to find something, worst case, you have to look through everything to see if it's there or not. Because if it's not there, you won't know until you've looked at everything, right? So that's an O of n algorithm, looking through everything to see if something is there or not. And I can make that better. You know, if I have a sorted array, I can perform binary search and get O of log n out. And again, we've talked about this before. But even with a sorted array, you know, now I have maintenance I have to do on it. I have to make sure it is always sorted, right? So if I'm changing the elements in it, if I'm adding stuff to it, I have to do so in a way that maintains it sorted so that I can continue to perform binary search. Otherwise, I go back down to my O of n algorithm and do this unsorted search through it. So it's really not fast. And a lot of times you can find yourself in a situation where you're asking an array over and over, do you have this element in you, right? So let's pretend like we're in a situation where we're looking at numbers one at a time, and we want to identify numbers that we have not yet seen. So we have an array outside of our loop that's holding all of the numbers we've seen already. And every time we see a new number, we ask that array, hey, do you have this number I'm looking at inside of you, right? And to answer that question, if that array is unsorted, it has to look through, you know, worst case or even average case, has to look through every element in that array to figure out if that element exists inside of that array. And that's really, really slow, right? So that's an O of n algorithm every single loop you do. So if you're doing n loops and you're doing O of n things each time, now you have an O of n squared algorithm, which is quite slow and not ideal. Arrays are also not great at adding elements that exceed the allocated length, like we talked about. We have to go find a new memory in our computer somewhere that has enough to keep all of the elements adjacent to each other so that the array can continue to have adjacent indices in memory. All right, so arrays are also not great at inserting elements into an array, and this is true when we're inserting at specific locations. So I want you to pause for a second and think about, you know, where would be the worst place to insert elements into an array, given what we know about arrays already. Where's a bad place to insert in terms of time complexity, and why? All right, so pushing at the end of the array is actually not bad, right? So given that we have enough memory allocated already to put new things at the end of my array, pushing at the end of my array is fast, O of 1. However, if I want to insert at the beginning of the array, what I actually have to do is shift everything to the right of that location over. So if I'm even inserting in random parts of my array, you know, average case, I'm probably inserting somewhere in the middle. And so I'm doing, you know, n over 2 shifts to the right just to insert a single element. So if I'm doing that, and you know, O of n over 2 is O of n. I don't care about constants and multipliers. So I drop that over 2, and I have an O of n algorithm for inserting at this point because I'm shifting everything to the right of that insertion point over to make room for the new thing. And you know, let's take a look at that actually. So we have our array again. All right, so here's my array, and it's filled with numbers. And let's say I have 3, 2, 9, 7. All right, and I want to insert a 1 at the very beginning. I can't just, you know, make a new memory location here. That's not allowed because I don't know if that memory's free. Okay, that's not how arrays work. I can't do that. So what I have to do is shift over everything to make room for this 1. And then once I've shifted those over, now I can put the 1 here. Of course, the 3 will be here, and the 2 will be here, 9, and 7. All right? So to insert an element, I had to shift indices over to the right, and the number of shifts I had to do was the size of my array. So that's why I have another O of n algorithm there. All right. Cool. All right, so when do we want to use arrays then? So there are a bunch of things we've learned that arrays aren't super great at. So when do I actually want to use them? So if we're holding ordered data, it can be okay because we can use binary search on it. If we're holding data where we know the index of where we're looking for, or what we're looking for, if we know the index of the thing that we want, that's fine because I have that really great O of 1 lookup time for random access if I know the index where the thing lives. And another time you can use arrays if you have a bunch of stuff that you need to do something to every single element in that array. So if I want to map over an array or do something to each element in the array, arrays are fine because I have to go through everything anyway, right? And because arrays are adjacent memory locations, it makes it pretty efficient because my my computer can just go, you know, memory block to memory block. It doesn't have to jump around to different memory locations. It's just going through sequentially, which is nice. So there are times now that we realize we probably shouldn't use arrays given these characteristics we've talked about. For example, if we're holding a bunch of random things, that we frequently have to ask that array the question, do you have this value inside of you, right? Like we talked about previously with an array of numbers, and we're looking at a new number and seeing if we've seen it already. That's a time where we probably shouldn't be using arrays because we don't know what index the numbers we've looked at before are in. We would take a long time to do it, like a dot includes or dot include, or dot find, whatever method in the programming language of your choice that will just do a linear search that array. That's not going to be fast if I'm doing it over and over and over again, especially if I'm working with a large array. And insertions, right? If I have an array, or if I have a bunch of data and I want to insert elements into it at a location other than the end of the array, an array is probably not my greatest data type for that. I might want to use a linked list or something like that, because my arrays, when I insert into the beginning, that's an O of n algorithm for that. All right, cool. So let's move on to hashes and sets and kind of see how they solve some of the problems that are created when we work with arrays. And you can use this in the example that we've talked about previously, like if I'm trying to see if I've seen a number already, this example we keep talking about, I can use a set instead of an array, and it will greatly reduce the runtime of my algorithm, and we'll talk about that in a little bit. All right, so first of all, what are hashes? We're going to talk about hashes, and then we'll kind of relate what hashes are, or what sets are in terms of hashes, and they're actually relatively similar in a lot of ways. So what are hashes? And hopefully they're more than just key value pairs, if that's what you were thinking to yourself. Yes, they are key value pairs, right? So they're a collection of key value pairs. You might know them as dictionaries if you're working with Python, or objects or maps in JavaScript. But they're more than just that, because we're going to talk about how they work under the hood today. So to understand how they work under the hood, we first have to understand the concept of a hashing algorithm. And this is how hashes got their names. So hashing algorithms, they are used in more applications than just hashes. You'll see them being used in cryptography and in cybersecurity, but we're going to talk about them today, not only in a very primitive sense, but also in the context of hashes. So again, we're not going to dive really deep into hashing algorithms. There's some complex design criteria that's behind these algorithms, but we're going to talk about them in their simplest form today. So the way that we're going to understand a hashing algorithm today is just as an equation that takes in data, and we're going to assume that this data is something simple like a string. So let's assume that the input to our hashing algorithm is string, and it's going to be converted to some number, some numeric output. Now, frequently you'll see it being a hashing algorithm output like a hex digest. But for now, again, very simply, we're just going to say that a hashing algorithm, takes in a string, and we're going to say that it spits out some number. And now, one extremely important design criteria that makes a hashing algorithm is that every time I input the same string, I have to get the same number out. Okay, say that again. Every time I put in a unique value, I have to get the same unique output. Okay, now the outputs don't have to be unique for input. So I could put in two different strings and they might give me the same numeric output. That does occur. It's not ideal, but just the nature of a hashing algorithm, that will occur. It's called a collision. But the important thing for a hashing algorithm to work at all is that every time I put in a certain string, I have to get the same output. Okay? So if I put in the string hello world, I have to get out 523 every time. Okay? Cool. All right, so we're going to talk about how hashes are made and what they can do for us. And they're actually built using arrays. Okay, so arrays are actually under the hood of a hash, and they give us some cool functionality in our hash that we don't really get with just arrays. So we're going to try to logic through how we think this works, and we'll see if we can come up with it on our own, and then we'll look at some examples. All right, and really quick, I told you I would tell you about sets. So you can think of sets as just hashes with no values, just keys. Okay, so hashes are a collection of key value pairs. You can think of sets as hashes, but they're just keys. So differences between a set and array then would be that sets are unordered, arrays are ordered, sets are unordered, and that sets can't have duplicates, just like your hashes can't have duplicate keys. Okay, but sets function very similarly to hashes if you just had keys. So that's how you can think about them. All right, so let's try to logic out how we could make a hash using arrays. All right, so let's first talk about our goal. Our goal is to achieve an O of 1 lookup time without knowing an index number. So I want to have just a key and use that key to get the value in O of 1 time. And for a set, I would want to use the key to see if it's inside of the set in O of 1 time. So I'm asking the set the question, do you have this key? Right? Same with the hash. I can ask the hash a question, do you have this key inside of you? And I want the answer in O of 1 time. Well, in an array, if I ask the question, hey, do you have this value inside of you? It needs to look through the entire array if it's unordered, right? So that's an O of n lookup time. So with hashes and sets, I want to use arrays to achieve an O of 1 lookup time if I know the key. Okay, so in order to do that, first let's identify what aspect of arrays that we've discussed already allow an array to obtain information in O of 1 time. So it's going to be that aspect of the array that we want to take advantage of. So what have we talked about with arrays so far that allow O of 1 lookup time? All right, so pause and think about it. And that's going to be random access using an exact index. So if I know the index of a element in my array, I can get that element in O of 1 time because all my computer does, like we talked about, is calculate the memory location and just go right there. Okay? So if we're going to use this O of 1 array random access lookup when I'm trying to get key value pairs or set key value pairs in my hash, we need to break this up into a series of functions, right? Anytime we solve a large problem, we want to break up the problem into a series of subproblems that we can solve easily. So we want to combine a few functions together to give us our whole output. So we need to identify what are the inputs and outputs of this O of 1 lookup time for my array. So in order to get an element from an array in O of 1 time, what is the input that I need and what do I get out? Go ahead and pause. Okay, so my input is going to be the index of where that element lives, right? So the cubby number where my stuff is. And the output's going to be the actual stuff in the cubby, or the actual value of what lives at that index. All right? So when I have a hash, I want to achieve a key value lookup in O of 1 time. What are the inputs and outputs of that? So if I have a hash and I want to achieve a key value lookup, what are my inputs and what are my outputs? All right, so here's another function we're going to want to take advantage of. All right, so the input's going to be your key, right? Because you want to get a value from a key. So the input's the key and the output's going to be the value that you get back. All right, so if I want to use the random access lookup time of my array random access inside of the function that I use to achieve my key value lookup in my hash, what data transitions have to occur so that my inputs and outputs all work together? And let's actually draw this out. You can pause it and think about it on your own if you want. But let's draw it out and take a look at what this looks like visually. And I think it would help to give some intuition. All right, so I like to think about functions sometimes primitively as a box, right? A box with an input funnel and an output funnel. I'm a very bad artist, for the record. All right, so we're going to say here's our input funnel and here's our output funnel. And this function is going to be our hash key value pair lookup. So we identify the inputs and outputs of this as a key goes in and a value comes out. All right, and so what I want to do is figure out how to use my array random access lookup time inside of this function to achieve an O of 1 runtime for this process. So we said that my array random access function has an input and output as well. So the input we said was going to be a index location, Okay, and then the output we said was going to be the value that lives at that index. All right, so data transformations that have to occur, I have to somehow use my key to get some index and use this value here to get the value of my key. So first we can assume, let's just say that the value that was stored inside of my array is the value for my key. So I can just plop this funnel output directly into this funnel, and I'll get the value from my array will be the same as the value associated with this key. So now our problem is, okay, so we had our key, it dropped down into our little box here of our args. So our arg is my key, and I need to somehow transform this key. So this key has to go into some type of transformation to become an index. Okay, so that's how I'm going to make these functions work together. All right, so and that's the data transformation we're talking about. So I have to somehow transform this key into an array index so that I can get the value in O of 1 time. Okay, cool. So we still have an unanswered question. The question is, what is this transformation? All right, so let's figure that out. If my computer works with me here. There we go. All right. Cool. All right, like we said, the data transformation was a key into an index number. All right, so the missing link then is how to turn the key into a number. Well, we talked about a hashing algorithm before, and we said a hashing algorithm takes in a string, and we're going to assume our keys are strings for now, in the same way that we assume hashing algorithms only take in strings. So we're going to say that our key is a string, so that transformation that we talked about is actually going to be our key going through a hashing algorithm and spitting out some number. Okay, so this missing link right here is our hashing algorithm. Okay, now the question you might be asking yourself is, okay, well, how can I be guaranteed that this hashing algorithm spits out a valid index that will work with my array? Right? That's a fair question to ask. So take the time right now, really quick, to see if you can think of anything I can do to a number to ensure that it falls within a certain range. Can you think of anything that does that? Right? So let's say our hashing algorithm can spit out any number whatsoever. Okay? And we want whatever number gets spit out to somehow be transformed into a number which is a valid array index in the array that I want O of 1 lookup time for, where my values live. All right, and if you said modulo, you're correct. Okay, we're going to be using a modulo at the output of my hashing algorithm, and we're going to modulo the output of my hashing algorithm to the length of the array, and that's going to guarantee that the result of that modulo will be a number between 0 and the length of the array minus 1, thus a valid index. And we'll talk about modulos in a second, so if you're not tracking me with modulos, that's completely fine. We'll go over that. All right. And put the solution together, what do we get? Well, we get what I just drew out. Okay, so let's kind of dive into that and explain this out. All right, so if I'm making a hash, I start out by allocating a large array behind the scenes. Okay, it would have to be large for right now. For this simple demonstration, we're going to pretend like the size is 10. I would ideally want it to be very large, and I would want it to be a prime number. And we'll talk about why prime in a second, but we're actually going to skip that for now. So here's my array. Okay, so the first thing I do when I'm instantiating my custom hash is I make an array. And again, this should be a lot longer in prime, but for now we're just going to say it's an array with a size of 10, all filled with nil values. All right, so when I put my key in, I'm going to put my key through a hashing algorithm, and it's going to turn this key into an index of the array. So my hashing algorithm of hello may spit out a number like this, 2838193. And you should be saying, okay, well, that's not a valid index of my array. And like we said before, we're actually going to use modulos to get a valid length. So if I modulo this by 10, I'm going to get index 3, and that most certainly is a valid index. So if I want to set a key value pair with the key of hello, the value is going to live at index 3 of my underlying array. And let's take a quick aside to go over modulos and make sure you understand them. All right, so modulos. There are a few ways to think about modulos. The most common way that they're talked about is the remainder of a division. So let's say I say like 10 divided by 2. Okay, 10 divided by 2 is 5, remainder 0. Okay, so if I said 10 modulo 2, because the remainder was 0, the answer to this modulo would be 0. Okay, if I said 10 modulo 3, the answer would be 3, remainder 1, right? Because 3 times 3 is 9, which has a remainder of 1 to get to 10. Or sorry, that's divided by, sorry. So 10 divided by 3 is 3, remainder 1. 10 modulo 3 is thus going to be the remainder of this division, 1. And this is commonly how modulos are described. It's not wrong, but it's not my favorite way to think about it. So let's think about modulos instead of remainders to divisions. Let's think about modulos as taking all of the numbers from negative infinity to positive infinity, so this infinite set of numbers, and mapping it to a set of numbers between 0 and the modulo minus 1. So let's say that I'm moduloing by, and so we'll say 0 is right here. All right, so let's say I'm moduloing by 3, okay? If I'm moduloing by 3, I'm going to map every single number from 0 to infinity to either 0, 1, or 2. So 0 would map to 0, 1 would map to 1, 2 would map to 2, 3 would map to 0, 4 would map to 1, 5 would map to 2, and then keep going, right? 6 to 0, 7 to 1, 8 to 2. And then, you can see why the other definition works as well, because we can easily tell that if I divide any of these numbers by 3, the remainder I get will be the number that we got here on the portion of the circle that we're at. So, 6 divided by 3 has no remainder because it divides evenly, so I'm at 0. 7 divided by 3 gives me a remainder of 1, which is why it's mapped to 1. And then, 2, 5, and 8 divided by 3 give me a remainder of 2. Okay, so I kind of like this thought process better of taking any number and wrapping this set of infinite numbers around a circle, all right? And the segments of the circle will be the same number that you're moduloing by. And the numbers will be from 0 to 1 minus the number you're moduloing by. So let's say, let's kind of do this again with a few more numbers. Let's say I'm moduloing by 10, and hopefully I draw this out right. It's not going to be pretty. All right, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so if I'm moduloing by 10, I'm going to wrap my numbers from 0 to infinity around this circle and map them to the numbers 0 through 9, okay? And remember, in our example, our array was of length 10, so this is kind of what we'd be doing when we get our hashing algorithm output. We'd be wrapping it around this circle, so whatever number our hashing algorithm output was lands on one of these valid indices. So let's say the output was 16, okay? So 0, 1, 2, 3, 4 all maps to themselves, right? And we're not going to talk about negatives today, but it does work. All right, so 10 will map to 0, 11 to 1, 12 to 2, 13 to 3, 14 to 4, 15 to 5, and there we go, 16 to 6. So if my hashing algorithm output was 16, my index that I save at would be 6. Okay? And that's how we're going to complete this idea of transforming our key to an array index. All right, so let's just start at the beginning so we're all on the same page here. So we start off by instantiating a large array, in this case 10, just because we can visualize it. But we instantiate a large empty array, and when I want to set a key value pair, I take that key, I pass it through my hashing algorithm to get some number, and then I map that number to a valid array index by moduloing by the array length. Okay, and now I have a place to save the value associated with this key. So when I say my hash with the key of hello equals the value world, my array behind the scenes now looks like nil, 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 world. So index 3 is now filled with the value, and the rest are still nil. And because my hashing algorithm will always output 2838193 every time I put the word hello in, that means that when I go to get the value for the key hello, all I do is put hello back through my hashing algorithm, modulo it again, and I know that the value of my key hello lives at index 3. Okay, and now I can use my array O of 1 lookup to get the value of my key. So I'm using the fact that if I know the index where my value of my array lives, I can get it in O of 1 time. So now if I know the key, I simply hash it and modulo it by the length of my array, and I now know where it lives in my array, and I can get the value in O of 1 time. Okay, and you might be thinking to yourself, okay, so this array has only 10 elements in it. So, and you might also have realized with our circle that multiple numbers, line up to the same, they'll be wrapped, because it's wrapped around so many times, you're going to have multiple numbers lining up to the same output of my modulo. And this does occur, it's called collisions, right? So if I put in a string whose output was 13, I would also get an array length of 3. And that key might not have been hello. So now I have two keys trying to save their value in the same index location. And there are a few things we do to try to stop this from happening. First of all, make our array very, very large to the point where I should never fill up the array more than about 70%. And I also want to make the array a prime number so that no patterns in the hashing algorithm will manifest in the array locations. Okay, because when I modulo by a prime number, for example, if I didn't have a prime number here and my hashes outputted evens disproportionately a good amount of the time, then I would be filling all my even numbers up in my array, and I'd effectively be only using half of the size of my array. So if I use an odd number or a prime number as my array length, I'll be making sure to evenly distribute my values inside of that array and make sure that I'm using the entire array. And the fact that my array is large will make the probability very small that I'll have a collision. And then, real hashes to have code in place to make sure that if a collision does occur, they might save like a linked list inside of this array and save both values there associated with the key. But we're not going to worry too much about that. Today's all about understanding the basics of how hashes work. So really focus on the fact that I'm taking a key, I'm hashing it, I'm moduloing by the length of the array, and that gives me the exact index of the underlying array where the value lives, so I can set it and ask to see if that key exists in O of 1 time. Cool. All right, so what are hashes good at? O of 1 lookup time if you know the key. Same thing with sets. O of 1 time to check to see if something is inside of a set, which is different than an array. Remember, if I have an array full of numbers and I'm saying, hey, do you have a 7 in you? That will take O of n time to figure out. With a set, I say, hey, do you have a 7 in you? Or do you have the word hello in you? That can be answered in O of 1 time, because all I have to do is hash the word hello, get the output of the hashing algorithm, modulo it by the length of the underlying array, and then look directly at the index where that value would be stored. And of course, with a set, you're just storing the key there because there is no value. So what are the drawbacks? You're using a lot more memory, right? So right off the bat, you're allocating this huge array under the scenes. So a lot of times when we get speed, sometimes we have to sacrifice memory, and that's exactly what we're doing here. In order to get that O of 1 lookup time that I don't have with an array, I have to use more memory under the hood to achieve that. And then, of course, collisions are a big deal. Again, I don't want to focus on it today, but if you don't take the proper precautions to reduce the number of collisions, and you're just saving, all your collisions in a linked list at that particular index, you could potentially find yourself back in an O of n lookup time for your hashes and sets. All right, so when should I use a hash or a set? And we kind of talked about this multiple times already. So let's go back to our example of I'm looking at a bunch of numbers one by one, and I want to keep track of the ones I've already seen, and I want to answer the question, have I seen this number before? So when we talked about it in the first time, we were using an array to hold all the numbers that I've seen before, and every single time I got a new number, I had to perform an O of n algorithm to see if I've seen that number before, because I had to search through the whole array. And you know what? Let's use words instead of numbers, just because we're talking about keys being strings and these set and hashing things that are strings. So I'm looking at I'm getting a new word one at a time, maybe every word in the English dictionary, and I'm trying to figure out if I've seen this word before. Okay, so instead of having an array that's maintaining the words I've seen before, which I would have to search through the entire array, I'm maintaining a set. Okay, so my set is maintaining all of the words that I've seen before. And when I see a new word, instead of looking through the whole set to see if I've seen that word already, all I do is I put that word through a hashing algorithm. I modulo it by the underlying length of the array inside of the set, and I look directly at that array location. If there's something inside of that location, then I have seen the word before. If there's nothing inside of that array location, I have not seen it. And now I've answered that question in O of 1 time, which is very powerful. You can the easiest way, to transform your algorithm from an n squared to n, and sometimes is by switching arrays to sets if you're doing it in the appropriate location. Okay, so keep that in the back of your mind. Am I searching through an array over and over and over again? If so, consider using a set or a hash. All right, cool. So let's go to a coding challenge where we make our own hash. We're going to do it in Ruby. Okay, so we're just going to pop open an editor, and we're going to try to code out a class that works just like a Ruby hash, obviously a very primitive version of one, but we want to see if we can get the same functionality and if we can achieve this O of 1 key value lookup and set time. So feel free to pause, try it yourself, but what I'm going to do is do it with you here. So if you want, you can just follow along. And this is not pre-rehearsed, so we're going to see if I make mistakes, we're going to do some troubleshooting too, and I think that's good practice. So let's get started. All right, so let's open up a directory. Actually, let's make a directory for this. So I'll say hashes, sure, why not? Actually, let's say code practice. All right, I'll cd into it, and I'll say touch. We'll call it rhash.rb. Can't call it hash because there's already a class called hash in Ruby, and we don't want to monkey patch it. We want to make our own. Cool. So we'll wait for VS Code to pop up. All right, and it popped up on my other screen. There we go. Cool. All right, so right off the bat, we know we need to make a class, right? So let's just do what we know we need to do. And cool. So our class is made, and now we want to instantiate. So if we make a new hash, let's just have no input arguments for right now. We just want to say like rhash.new, right? And not worry about putting any input arguments in. If you're familiar with Ruby, you can say like hash.new and put in like a 0. And basically what that will do is if there is no key there and you look up a key that doesn't exist, it'll give you back a 0. So basically what that's doing is it's filling, this is the value that it puts in every single element of your underlying array. Actually, you know what? Let's go ahead and do that. We'll default to nil, and we'll say, so init val, and we'll give it a default argument of nil. Okay, and then we want an underlying array, array.new, and we'll give it a length of 199. Probably not big enough, but at least it's a prime. And we're going to say we want 199 init values. So if they don't put anything in, it'll be 199 nils in our array. Otherwise, it will be 199 of whatever they put in. Okay, and this is cool because now whatever your init value is, if you hash a key that you don't have in your array and you look it up, you're not going to get nil, you're going to get whatever this initial value was. So a lot of times you'll use a hash to make like a frequency hash, like count how many times you've seen something. So if you make your initial value 0, you don't have to check to see if the value coming back from when you look for a key is nil, which would be otherwise. You can just add 1 to it. So if you've already seen it, it will have some number in there of how many times you've seen it. If you haven't seen it, it'll be 0, and you can safely just add 1 to it. Okay, so let's go ahead and start by saying, okay, so I know I need a hashing algorithm. I need to have some way that I'm going to turn a string. Again, we're going to stick to strings here. I want to be able to turn a string into a number, numerical output. So let's think about that for a second. So I'm going to actually go into IRB down here, a little interactive terminal, and we're going to play around with stuff and see what we want to do to achieve this. Okay. Now hashing algorithms, like I've said before, they're pretty extensive in terms of like the design parameters. All we're really going to worry about is changing a string into a number and making sure the number is the same for every single string, and or not for every single string, but the number is the same per input. So a input will always give me the same output, like we've talked about before. So we want to do that, and we also probably want to make it not terrible. So let's see what we can do here. So one nice thing that I can do is I can say dot bytes, which is pretty cool. It gives me an array of bytes. In Ruby, I can also say each byte do, and I can get this number one at a time. So if it just puts out this byte, you can see I get these one at a time. So either one of those is probably a good starting point. So I get an array of numbers. One thing I wouldn't want to do, right? So off the bat, it might be tempting to be like, okay, well, I can get a number from this by saying test.bytes.sum, right? And that'll just sum up all of these. And every time I put in test, I'll get that same number out. Looks good. We're not going to do this because, if I just take the same letters in a different order, that's going to give me the same number. So let's not be that terrible when we make our hashing algorithm. Let's try to make it so the index, so the location of the letters have some sort of input into how I do this. Okay, so one thing I could do is actually go ahead. This will be a time that you can pause if you want to and try to figure it out yourself. There are a few ways you can do it. Again, like you don't want to do anything crazy. This is just more about understanding than anything. But basically, we want to do something to show that the letters are in a specific order. So let's go back to our test.bytes. Oops. Test.bytes. Okay, and I'll say dot each with index. So now I'm going to get the bytes with the index of where they live. So bi are the two things I get from it. And now let's just say b times I plus 1. Okay, and I'll say sum plus equals. I should have said sum equals 0 at the end. Okay, but I'll have sum, and I'll add to my sum. Instead of just summing up everything like I did here, I'll sum the product of the index plus 1 so that we're not just negating the first index because it'll be 0. So I'll sum the product, and again, this is just something I'm trying to come up with on the fly here. So I might not be the best, but it's something that should do the trick. And this is going to error out because I never defined sum. All right, so let's do, I don't want to use reduce just in case you guys aren't familiar with it. So let's just do this simply. So I'm going to say sum equals 0. I'll say test.bytes.each with index do. I'm going to get my byte and my index, and I'm going to say sum plus equals b times I plus 1. Okay, cool. And now if I look at sum, I have this number. So now let's try that with a different ordering of this number, like I did before. And I didn't clear out sum, so let's say sum equals 0 first, and then do that. All right, so as I can see here, sum is now different than it was here. Okay, it's not perfect, but at least it's protection against like the really simple thing of just different orders of numbers. So let's make that our starting off primitive hashing algorithm. And I'm thinking it might be a good idea too. After we get this working, I might do a little bit more if you guys are interested, a more complex example of how to make this hash and do some of the other things that hashes will do. But let's start out with this. So I'll say def hashing algorithm, and it's going to take in some word or some key, okay, and it's going to spit out some value. So let's say that we want to say k.bytes.each with index do. We're going to get our byte and our index, and we'll say sum equals 0, and we'll say sum plus equals b times I plus 1, and then we'll return sum at the end of the day. All right, cool. So let's give this a shot, all right, and test this out a little bit. So I'll say word1 equals test, and we did this in the terminal, but let's just make sure that it still works. Est, and then word3 is something completely different. All right, so let's go ahead and just puts out. So we'll have to instantiate our r hash. H equals our hash dot new, and we'll put out h dot hashing algorithm, and we'll make this a private method in a second, but we're just testing this out. W1, and we'll do this for W2 and W3 as well. Let's just see what we get. All right, so we'll say Ruby our hash.rb. Cool, 3 unique numbers. Perfect. Okay, so I think this works for now. Let's just keep this and move on. So if we're okay with this hashing algorithm, we'll go ahead and make it private so we can't call it outside of the class. It's just good practice to hide methods that we don't want people outside of our class to be working with directly. Okay, so we'll go ahead and make that a private method, and now let's make a method that can set a key value pair. So I'll say set kv. It's going to take in a key, take in a value. Okay, and so now what we want to do, and let's do some pseudocode here, right? So just to break it down, we want to hash our key and modulo by the length of array, and then we want to store our value inside of that index. Okay, so what we're going to do is we're going to say index equals hashing algorithm of key modulo array.length, and then we're going to say add array of index equals value. Okay, cool. Get rid of our pseudocode. Code should speak for itself, right? And this looks pretty good. So I could put this, directly inside of here, but I think this looks a little bit nicer, easier to follow. So let's test this out. So I'm going to say r equals r hash, capital H, I think. Excuse me. All right, so r equals r hash dot new, and let's just set the key value pair hello world. So I'll say r dot set kv. Hello world. All right. In order to test this, let's go ahead and make the one that gets the key. So get or def get value of some key, and this is going to be pretty much the same thing, right? Index equals hashing algorithm of k modulo array.length. I'm getting that same index, and then I'm just returning array of that index. Okay, so I should now be able to set a key value pair and then say get value of hello, and if I put this out, it should say world. Oops, didn't use add array, and I don't have an attribute accessor or reader or writer, and that is on line 16. Add array. Cool. All right, there we go. We got world out, which means I successfully set hello world. All right, let's try that one more time with a different key value pair. r.set kv, and I'll say coding is fun. And then I should say puts r.get value of coding. Oops. All right, and I should now see the to pronounce world and is fun. Very cool. Okay, so it looks like that's working pretty well. Let's do one quick little trick before we move on to anything more sinister, I guess, in terms of making this a little bit more complex. I don't really like that I have to say set kv and get value. It's kind of like not super Ruby-y. So let's make this work like our actual hash. Okay, so let's say setting a key value pair. So like if I was using a real hash in Ruby, right? So if I said like h equals some hash literal, and I want to set hello world in my hash, it would be like this, right? So I want this same functionality here. So really what this does, and let's actually do this in the interactive terminal because it's kind of cool. So really what this does is Ruby is different than other languages in that everything is an object. So really when I say h of hello, or sorry, I didn't even define h. Okay, so I define h, and when I say h of hello equals world, right? And I can now say h is hello world, right? So what I can do instead, what really is happening when I write that syntax, that's really just syntactic sugar for a method called bracket bracket with 2 arguments of hello and then I'll say goodbye now. And this should change my value for the key hello. Bracket equals, my bad. So, right, so the method is bracket equals for setting a key value pair. That's the actual method in Ruby. And just like, I don't know how familiar you are with Ruby, but if I want to access this array, you know, I get an error when I said just array here, when I didn't use the instance variable. If I wanted to access that, I would have to make a reader, so a method called array, which just returned array. You know, I could use the attribute accessors macros, but we're just going to do it manually here. And then if I wanted to be able to write to array and change its value, I would have to write an array equals method that I passed in a new array to, right? And you would get add array equals new array. Okay, so in the same kind of pattern here, Ruby, when you're setting a key value pair like this, that's just syntactic sugar for this method right here of h bracket equals being the method name, and then it takes in two arguments, hello and good, your key and your value, right? Value, right? So I'm changing my value here. So all I have to do to mimic this, instead of set kv, I just need to write a method called bracket equals. And then it's the same thing with getting a value, right? So if I want to get h of hello, this is the normal way you'd see it be done. But really it's just h dot, the bracket is the method name, and then the argument is the key, and I get the value. So if I want to have that same functionality here, I just make a method called bracket that takes in the key, okay? And I can tell it what to do, just like I was doing before. So now I can use this syntactic sugar in my code, now that I've made the method names correct. And I'll start by showing you like the not pretty version, okay? So we'll do this first. And this should be equals, because I'm setting key value pairs. And instead of get value, it's bracket, okay? Get value, bracket. So I should see the same two outputs that I saw before when I run this. Right, world is fun. And now I can do the fun part where I actually take my key, put it inside of here, and utilize this syntactic sugar. All right, so I get r of hello equals world, r of coding equals is fun. All right, and I drop my thing. There we go. All right, and then let's put these again. Puts r of hello and puts r of coding. All right, and if I run this again, now I did something wrong. Let's see, unexpected bracket. Oh, because I still have my dots. All right, you take your dots out, obviously part of the syntactic sugar. Okay, so I'm now able to use my syntactic sugar here. Let's get rid of the h because we're not really using that at all. And I'm able to use this custom hash that I wrote, not only to achieve O of 1 lookup time in terms of getting a value from a key, but I'm also able to write methods that let me use it in a really good looking way. I want to do one more thing real quick to show how we can use more than just strings as keys. So what we're going to do is we're going to modify our hashing algorithm method to accept more than just a string. So in order to do this, I have to have a few if statements. So I'm going to say if my input key here is a integer, I'm going to do something. Else if k is a string, I'll do something else. And else if k is a symbol, I'll have another strategy for that. And then finally, what do I do with everything else? Okay, so let's think about it. So integer, we want to output an integer, so let's just for right now return k. I'll use an explicit return here for fun. For the string here, let's do something a little bit different. So before, what we did is we in order to differentiate a series of letters that were in different orders from each other, we multiplied by the index. What I want to try doing this time is taking the bytes and concatenating them as a string, and then turning that concatenated string, into an integer, and that way we'll be also maintaining order in that sense. So let's take a look at that. So I would say t equals test. T.bytes gives me that array. But what I'm going to do this time is say t.bytes.join as an empty string. So I now concatenate those bytes together as a string. And if I now just turn these into an integer, I get this unique integer out. So let's do that this time. I think that'll be a little bit more fun. So I'll keep doing my explicit returns. So I'll use k.bytes.join .2i. And then finally, if it's a symbol, I'll just do the exact same thing, except I'll turn it into a string first. Okay? And then finally, what do I want to do if it's some random object? Okay, so if it's not one of these three things, I'm not sure I can tell the equality between the two. All right, so I don't want to take the chance that somebody puts in as a key some object which doesn't have equality built in. So what I would want to do, let's say I have a class of dog, okay, and I say d1 equals dog.new and d2 equals dog.new. What I want to do is let's use the object ID of these things so that if one of these objects gets passed in as a key, it has to be the exact object. If you want to find the value, you're not going to check the quality of, like, for example, d1 and d2, because dog has no attributes. You could call them equal because there are no attributes there. And if you wanted to do something like that, you could marshal the objects and serialize them, and then go from there. But instead, I think what I'm going to do is use the object ID. So what I'm going to do is here in the else, I'm just going to say return k.object ID. And I should now be able to use any of these types of objects to create a key value pair. So let's try it. R of test equals yay. R of... Now, here's the problem. This test and this test will overwrite each other. So what if we just, for the symbol, said bytes, and let's map these bytes to, let's say, times -1 plus 1. I don't know if that's a great algorithm for this, but let's just give it a shot. All right, so we'll see if those are different. Yay 2. R of 10 equals 74. Okay, and now I want to say puts R of test. I should get yay. Puts R of test should give me yay 2, and puts R of 10 should give me 74. So let's try running this and see what we get. Yay 2 and 74. Cool. So, and that's a very simple way. Obviously, like I have said a few times now, this is not like a hashing algorithm you should be using in real life. But hopefully it describes how hashes actually work under the scenes and gives you a better understanding of the fact that your key value lookups, and for your sets, just your key lookups, are happening in O of 1 time, and how that actually works under the scenes. It really doesn't take that much code to build a primitive form of it. All right, guys, thanks for tuning in.